So learning objectives in this segment: understand how manometers measure pressure, understand and recognize intensive and extensive variables. Those talked a little about in chapter 1, but we're going to revisit it more because it's relatively important it's important to conceptualize how the ideal gas law works. Understand how the ideal gas law relates to other gas laws. So that's what we'll be doing in this segment. So first, if you look at a manometer, how does a manometer measure pressure? So the way it's set up, the original way that people measured pressure is you would have one end either open to the air or have some tube on it. And if the external open to the air or have a bulb on it, and then there's a U-shaped tube and then a liquid in the middle and then some bulb of gas on one side. So in this case, if the pressure was greater than 0.5 atmospheres, it would push down on that liquid and push the liquid towards the 0.5 atmospheres. So how can we use this to understand what the pressure is of the gas from here pushing down on the liquid? Well, there's a few rules that we can apply here. So rule 1, the pressure at any point in a liquid is, the pressure at any point is, not a liquid, just in general, is equal to the combined pressures of everything above it. So the force adds up from everything that's pressing down. You know, pressure is essentially force per unit area. So if you have a set area that has equal pressure across it, then the total force of everything above it comes from the pressure. Okay. Rule 2, the pressure must be the same at any 2 points of the same height in a continuous fluid. Because if they weren't, then the fluid would adjust so that the pressures would be the same. So so the pressure must be the same height at any 2 points and the same height in a continuous fluid. And finally, rule 3, because gas is far less dense than liquid, the pressure in a gas does not significantly change the function of height. So if we're looking at the height here between where the bulb of gas is and where the liquid surfaces are, we don't really count that height because the gases are so much less dense. There's much less mass pressing down. Okay, so we want to understand how are P1 and P2 related. So P1 is equal to P2 if we can trace a line straight across. So what we want to try to do is relate this height here, the difference between P2, the pressure at P2, which is going to be equal to the atmospheric pressure, and the pressure in the bulb there. So now let's have a different situation where we've got a bit more precise measurement. So we have gas of 1 atmosphere in one bulb. We open the valve so that that gas pressure is pressing against P1. So P1 equals 1 atmosphere. P3 is equal to 0.5 atmosphere. We have a gas at a pressure of 0.5 atmosphere in that bulb. And so the pressure at P3, the pressure of that gas, is 0.3. The pressure at 0.2 is going to be the pressure at 0.3, that's the pressure of the gas, plus the pressure due to the liquid that's above P2. So what's the total force there? It's going to be the gravitational force. It's going to be the height of the liquid times the gravitational constant times the density of the liquid. So that the density times the height will give the math. We go through the units, then density times acceleration times height as units of pressure. But P1 is equal to P2, and so therefore the difference is pressures. The difference in the pressure exerted by the gas in this bulb and the gas in this bulb is just enough to support a height of our liquid proportional to the density times the gravitational constant times h. So if the density of the liquid is known, then h can be calculated. If h is known, then the density can be determined. So if you know the density, you know the gravitational constant, and know the height, you can figure out the pressure differential between the two gases. So there's a good example. I'm not going to go through an example calculation of this, but if you go back to the discussion, the in-person discussion segment for the second lecture, then I work out how you can use this to calculate the height of a column of mercury. It does end up being exactly 1 160.3. So you can go through and look at, for lecture 2, I've posted the notes and I walked through that there.